name is Alon, and I'm going to be talking today about how you can increase the speed of your program writing the R statistical package. The real motivation for this is I've spent a lot of time both privately and in the professional sphere developing R code and R programs, and I've seen a lot of comments on forums and help desks about that R is slow. I'm here to demystify the fact that A, R is slow, B, it is very difficult and expensive to speed up R, and C, you have to be an expert to do it. Hopefully, using these simple examples, you'll be able to understand how you can speed up your increased code, and do not hesitate to email me or contact me if you have any questions. There's a few reasons why we like R, and I like R, and I use it both in the work environment and personal life. First of all, it's cheap, and this is a really big selling point of R. There are many other competitors out there, SAS, SPSS, that also offer similar services, but they'll often run you up to $50,000, $60,000 for the full suite that R gives you for free. Probably the strongest feature of R is its comprehensive dynamic library. R has a very, very extensive list of packages. It's numbering in the thousands right now, and any new advancement in academia or in industry, it comes to R first. And that's a really big competitive advantage. Another nice thing about R is it's flexible. It's built very modular, and the code is very open for you to input it in and change it as you will. R is built on a paradigm called functional programming, whereby when one uses an input to write a function, changing that input at a later point in the program doesn't change the output of that original function. This is sort of a quick and dirty. I fully admit I don't have a computer science background, but that's how best I'd explain functional programming. And the nice thing about functional programming is it's very linear. So you can see how you take your inputs, you transform them, and get outputs that you want without having to worry about third or fourth order effects on the entire system. Another nice thing about R is in its consoles, it gives you immediate feedback. This is especially an advantage over compiled languages such as Fortran or C++, where once you have all your code, you have to write it through a compiler. Often you have to write your own manner of seeing the output, of testing, debugging, everything. R does everything for you so that you know when you don't get the result that you're looking for. Another nice thing about R is that it's very robust. I personally killed R only twice, and that was due to Excel. It wasn't due to R. I've never had any issues with being able to run R. There's very good documentation. I've seen a lot of complaints on the internet about the way R is documented, but if you actually delve in and look at the details of this documentation, you can actually find it very helpful. You just have to be a bit patient, willing to read, willing to see cross sources, and it's actually a lot more helpful than in commercial services where you'll have very long stories but often very little content. And probably one of the greatest things about R is that it's very easily extended. So it's very easy for you to take the R platform and extend it to whatever use you want, be it monitoring, reporting, document information, anything else. So in theory, we should be very happy. However, yes, ladies and gentlemen, R is slow. Now this is an example I got from, I can't even pronounce his name, but I included a link to a site, and you'll see it in the website, and it shows a speed comparison between R, Python, C++, Scilab, MATLAB, Pure C for a expectation minimization algorithm. And as you can see here, R actually does pretty poorly. So especially on the small bits where you need to call the functions very quickly. So this is in the creation of the sample bit especially. You can see that R is quite slow, relatively speaking, to something like C or Pure C. Now, of course, this will be highly dependent on the algorithm that he wrote, and I don't know the details, but this corresponds generally to what people tell me and what is commonly accepted wisdom in the computer science world. If you look at the 10 expectation minimization component of this algorithm, you'll see that R actually doesn't do nearly as poorly in time as Skilab, as Python, as MATLAB. And that's a big deal. So the issue with R is there's a lot of wrapping that makes it very easy and very helpful to use, but it also makes it much slower because there's all these error checking, all the scope issues that other languages like C just don't have. But once you have all that information and you send it, and the actual number crunching, relatively speaking, R isn't that bad. And I'd also like to point out that on a human basis, this is in seconds. So you can see that even on a human basis, you're talking 1,000 seconds. That's just not that much. I mean, it's true if you're a high-frequency trader, that's a big deal. But for us in more domestic settings, the difference between 600 seconds and 1,200 seconds just isn't that big of a deal. So here are some possible solutions that we can do to speed up R. We can use parallelization, so these are most notably the Snow and multi-core packages. We can integrate GPUs, CUDA, OpenCL. We could write code in lower level languages such as C, Fortran, C++, RCPP, which is a very popular way to integrate R with C++ right now. You could get faster hardware, more memory, and newer CPU. You could create your own package because compiled R code is faster. Or you could just move to MATLAB. However, there are problems with those solutions. First thing is they're quite expensive, and this is actually a big deal either privately or within an organization, is especially for MATLAB with all the packages you could be easily running into $40,000, $50,000 a year, and that's just a lot of money. So they're not easily scalable. So the problem with compiled code, even MATLAB to some extent, is it's much harder to spread your tools and use them across large numbers of people under different computers in different scenarios. You'll need to, for MATLAB, you'll need to make sure that every computer is compatible, it has a license, and so forth. You'll need to pay for the license fees. For compile languages, the people who use it will have to know what a compile language is. They'll have to code in it, understand it, and that's very difficult. So another thing is they're difficult to keep track of. So the more sophisticated and complex your solution is, it's going to be harder to manage, and you're going to have to start doing project management, so documentation, coordination, making sure that all the linkages work, and that's very, very difficult and substantially adds to the cost of implementing any of these solutions. Another issue is that it's hard to document, so even if you know there's a solution available, the person who knows that solution may not be a competent writer or be able to communicate how they came to that solution. And it makes it much more difficult to link it back to that scalability issue. Another issue is substantially increases development time. Compiled code is just very long, and it's going to be 3, 4, sometimes 5 times longer than writing in R code. And when you're considering whether to use R code or compiled code, you have to factor in the lost time in development. This is another thing that's quite dear to my heart being in industry, is that the results may not be translated to meaningful time savings. So the difference between an hour and 15 minutes is quite substantial in human time, but the difference between 15 minutes and 10 minutes isn't nearly as significant. And so if you're putting all this investment into these complicated projects and you're not resulting in tangible human time savings, you seriously have to consider changing course of action. Another issue is it's risky. These more sophisticated, more elaborate solutions, they could break down. As you add more nodes to your tree, it's more fragile, and that is very risky from both the project management perspective and from a user perspective. And ideally, you want to eliminate that risk, and so that's why these solutions aren't necessarily the best way to approach things. What's my answer to those questions above? we have to write better code with a few R quirks. So the first thing we're going to talk about is to know the task at hand, to not repeat yourself, to pre-allocate space, to avoid function calls, to understand the syntax, to functionalize everything, to use primitives, explicit use of scope, to vectorize, to simplify data structures, to use packages, and I'll end with a note on the compiler package. All these solutions you should be able to do at home. They're very simple, and I expect that you'll find substantial time savings with them. One thing to note is that each one of these pages is only the conditional time savings, so together the actual time savings that you may get from your program may be more or maybe less. It depends, because they may be in conflict or they may be upholding each other. So the time that I save on these may not be typical of your experience, but they're a very good indication of the relative savings you can get. So let's talk about know the task at hand. This is a very big thing in computer science, and unfortunately a lot of programmers miss this fact, and this often causes difficulties between management and the programmers, is that often they'll forget or they may not even understand what the code is supposed to do. I highly suggest that you take a moment in your mind to think of the inputs, how the program uses them, and turns them into outputs. This is a really important point, is to discard what is unimportant. So all these other features, bells and whistles, optimizations, if they're not important to getting those inputs and turning them into outputs, forget about them. Don't work on them, because they'll just be a waste of your time and everyone else's. Another thing that you should consider is to avoid tacking on new things to an existing project. And this is very important, is to establish with the key stakeholders what is needed to be done and what is important. And be very firm in conveying to them that you do not want to add extra features, because that will substantially increase the development time. This is a statement for the more ambitious amongst us, is that you should write code that accomplishes what you're trying to do. Not code that is smart, fun, or creative. And this is a big thing for you whizzes out there, is that I'm sure you found a new technique or a new algorithm that you're really excited about and you really like. But it's really important to understand that unless those things solve the problem you're trying to solve, do not use them, because you're just going to waste time checking them out, debugging them, and integrating them into this problem which may not need that solution. Another lesson that you should take that should help you speed up your R code is not to repeat yourself. When programming, it is easy to be inattentive to the semantics. So it's very easy for me, I do this all the time, to think, well gee, every time I need to get the height of x, let's say, then I just call the function getHeightX, and this is just, an arbitrary example. The semantics, however, do determine what happens on the computer level. The time taken to calculate the height of x may not equal the time taken just to grab the value of the height of x. So a really important point is not to recalculate values that are not conditional on execution of the program. So if the height of x is only needed to collect it once, only collect it once, because afterwards you can just grab it from the memory. So here's an example. We're going to take a matrix of 1 to 1000 with 10,000 rows and 10,000 columns. So I have two syntaxes here, syntax 2 and syntax 1. Now if you notice, syntax 1, it grabs n row, the number of rows each time for the iteration, while syntax 2, it just grabs b.vec, which is the number of iterations of the program. And by the way, I just use system.time to compare all of the syntax, and it's a very useful function, very interesting. I highly recommend you check it out in R. So syntax 1 took 7.53 seconds, and syntax 2 took 5.74 seconds, for a time savings of about 32%, which is quite substantial. Another thing that you should do is pre-allocate your space. This is one thing that really changed my paradigm about R, was that unlike other languages, you do not need to declare the size of the array before calculating the result. So ex ante, you do not need to determine how much space you need. This allows us to dynamically expand lists and matrices, and it's very easy for writing very fast code. However, this feature comes at a significant computational cost. So my sort of tidbit from this is, when possible, determine the size of the resulting array ex ante. So here's an example for you. So syntax 1 does a cbind, while syntax 2 already has the matrix and it just fills the different rows with 1 to 1000, which is a vector. So let's just say I want to create a matrix of 1 to 1000 of 10,000 rows and 1,000 columns. So I just want to fill it up 1 to 1000 all the way down. So one thing I could do is cbind. Another thing I could do is fill up the values. The system.time comparison is 4.39 versus 0.12. So that's incredible savings. The simple rule of thumb for this is never use cbind and never use rbind. They're very, very slow functions in R, and if you ever need to save time, do not use them. Another thing that you should do is to avoid function calls in R. There's significantly more overhead in R functions than those of other languages, and I'm sure there are people that can get much more involved in this. Personally, I don't know the details of this, but I know that this is a substantial issue that may be changed in future versions of R. This makes repeated function calls bear a much larger penalty than in other languages that you may be used to, such as C. So a good note to take out of this is to minimize the number of function calls in R. So in this example, I have syntax 1 and syntax 2, and syntax 2 takes a uniform draw and draws them all at once, while syntax 1 draws them multiple times of 100. If you compare the system.time, you can see that for syntax 1 it's 0.89, while for syntax 2 is 0.52, for 42% in time savings. Now if you count the zeros, you'll notice that I drew the exact same number of uniform draws, but the big difference is the number of function calls that I made. Another thing to remember is to understand the syntax. It is always easy, because there is a lot of documentation. I understand how overwhelming it can be, especially for someone who's new to R, to just avoid it and read it entirely, and just run straight to the example. So they have those examples at the end of each function, and you just copy, paste, and see what happens. And it's very nice, but sometimes it can lead to misleading results. There are hidden features in many R functions that can substantially increase the speed of your code. So as a result of this, you should really understand all the parameters of the function that you're trying to use. So here's an example. So what I did here is I made a nested list of uniform draws. So it's a list within a list. So there's a list of lists. And I'm trying to unpack that. So I'm trying to unlist that just to get the uniform draws. So syntax 2 has unlist without using names. And syntax 1 unlists just vanilla as it's defaulted in the program. And if you compare by system.time, you see that syntax 1 is 0.37, while syntax 2 is 0.33. So you saved 11% right there just by using use.names equals false. And this is a really important point. I highly suggest you look into the different packages and the different parameters just to make sure that what you're using you need. Otherwise, just set it to false and you can save a substantial amount of time. Another thing that you should do is functionalize everything. I'll tell you what I mean in a moment. So the computer does not know the sequence of commands that you'll be giving it, because really a computer is stupid. It just takes what you tell it and it gives you the result. Only you know the specific features of the program that are important, what is needed, what changes, what isn't needed, what are the steps that are involved. The computer, it just takes everything as given. R is really designed for writing custom functions, and I really strongly feel that when the creators of it wrote it, they thought, how can we make writing functions as easy and intuitive for people as possible? A good mantra is always create separate functions to perform the computationally intensive part of the program. So in my example here, you take a uniform random draw, and in syntax 1, I take the mean of the standard deviation and the variance of that draw. In syntax 2, I create my own function, which calculates the mean, the standard deviation, and the variance, and it returns all three of those features. So when we do a system.time comparison, we can see that if I just did those functions, I would get 2.16 seconds. While if we used my function, we would do 1.27 seconds for a 41% savings. And the reason why we have those savings is because the mean, the standard deviation, and the variance, they all use the same calculations. So rather than recalculate everything every single time, you can just use one as an input into another using your function. So instead of just giving it to the computer, you tell the computer, listen computer, I know all these things. Use these things to help create what I want. Another thing you should do is use primitives. Our functions can be decomposed into various levels. Primitives are the simplest functions, and they directly link to the Fortran C code that underlies how R is written. Functions that are primarily written in R, when I say primarily, I mean that a substantial amount of the operations are done at the R level, are actually much slower than their respective primitives. So you should really always use primitives whenever possible, if speed is your primary concern. So this is an example. This is something that's very close to my heart, because I see on a lot of forums how people post slow syntax and complain, and they use if-else statements. Honestly, you should never use an if-else statement. The actual reasons why, I don't know. It's just a very slow statement, and often you can substantially increase the speed of it. And this is my example. So what I did here is I just took a bunch of random draws and split them out. If they're bigger than 0.5, they're 1. They're smaller, they're 0. And these both functions provide the same output. So when I do rProfile, and rProfile is a very smart R function that it shows you the amount of time spent in each sub-function within a function, so you can actually see how much time is accounted for different segments. And you can see that in syntax 1, you spend a substantial portion of time, of 0.22, in the if-else statement, just dealing with features that the if-else statement needs to deal with. If you create your own, you can just totally bypass that and save all those 22 seconds. And your time saving is substantial at 91%, and this is really, really big. Really, really big. Explicit use of scope. Scope is one of the more complicated concepts in programming that R makes easy. If a variable is not found within the current environment, then R looks for a variable in other environments. Searching for this missing variable uses considerable resources. So always explicitly use scope by passing a variable or declaring it within a function.